All right, hello everyone. This is Team CE14 presenting the replacement of our railroad bridge located in Stratford, Connecticut. Before we get into the details, we'd like to thank our two sponsors, Dr. Ahmed Fioklu with the DOT and our faculty advisor, Dr. Shanae Zhang. Both of them were really great helps with our project this year. So to get into it, currently there are 5 railroad bridges located between Bridgeport and Stratford that need to be replaced. All of these bridges are over 100 years old. Currently, they're all open deck structures. As I just said, these are very outdated. Their goal right now is to replace these with ballasted deck structures as a part of their track speed improvement project. So what they need from us are moment reaction tables for our structural members, a load rating analysis, structural quantities, and a full cost estimate of each of our members, such as girders, stringers, floor beams, etc. I'm now going to pass it along to Garrett to talk about the current structure and existing conditions of our bridge.
And so before we started our analysis, we needed to know what was going on with the existing structure, pictured as you can see here. So first thing first, we need to figure out the load path, which comes from where the train passes over the tracks. The load is carried then through those into the stringers, which passes through the floor beams and into finally the girders and the rest of the substructure, which we'll analyze later in a more quantitative way. But there's some other design and construction analysis we need to do for the surrounding area on the next slide. For example, when you're making a bridge and you're implementing it in construction context with a bunch of live wires overhead, that kind of limits your framework and ability to construct a bridge. Also, since we're less than 400 feet away from a neighborhood, there's a bunch of noise constraints we're going to have to comply with and accommodate those fittingly. And working on a train track, there's inherent challenges there where you need to have minimal amount of mobility impact time for affected trains going over your rails. And as you can see pictured here, that there's 9'9" clearance beneath the bridge, which is already small, which we're going to have to maintain, which is one of the key design features moving forward. And some workarounds we have building during non-peak rail hours, so like say the weekends, as well as accelerated bridge construction. Moving on to the final design, here's Mike.
So for this design, we are taking into account 2 major factors, AREMA, which is the American Railway Engineering and Maintenance of Way Association, and the Connecticut Department of Transportation. From the DOT, we've been using their bridge design manual, cost estimating manual, and their load rating manual on this project. The final design took into account several different load cases, the first of which is the dead load, which takes into account the weight of all permanent construction materials on the stringers, and then, like Garrett mentioned earlier, those loads are transferred through the floor beams into the girders. For the live load, we've used the Cooper E80 loading from AREMA, and AREMA provides a table that specifies the different moments induced in the structural members for different span lengths of the bridge. The impact loading was applied as an additional percentage of the maximum live loading, and impact loading has 2 sources, impact due to the vertical effects of the train bouncing up and down as it passes over the bridge, as well as rocking effects as it sways side to side. The wind load is calculated as a linear 300 pound per foot force acting horizontally on the train that creates an overturning moment, increasing the force on one rail and decreasing the force on another. And then finally, when we took all our load cases into consideration, we designed the stringers and the girders for this bridge. On the left, you see the stringers, which are W14 by 233, and the girders are a modified W14 by 257. And here's Matteo to talk about the project modeling.
Okay, so the 3D modeling was done using SAP 2000, which is a powerful structural design tool. From this image, we can see how all the structural components of the model, or we can see our girders, stringers, and floor beams. With the help of SAP 2000, we can corroborate that our hand calculations were accurate using many of the structural analysis tools, such as the shear diagram in Figure 1, which helps us visualize how the loading behaves on each member and eventually how the bridge behaves as a cohesive structure. Moment diagrams in Figure 2 help us see how the loading bends each member to eventually obtain a deflection diagram as shown in Figure 3. With the help of SAP 2000, the team was able to run an analysis under the load cases and show if any of the members fail. After the analysis, the results show that in this design, none of the members fail and the structure is safe. One of the design alternatives that the team proposed was a design that includes a series of lateral trusses using angle shapes. This design helps reduce the lateral forces on the bridge, but the team eventually chose the current design using only 4 floor beams instead of the 6 floor beams that the original design had.
And so a little bit more about implementation considerations. So we're primarily using accelerated bridge construction, which uses prefabricated modular bridge sections to not only decrease the amount of time on the project, but it also allows us to use a key assumption in using and designing these girders, where we can use the full moment capacity, plastic moment of all of these girders, because we can actually set our members in a concrete slab, which behaves more like a composite and allows us to put them in a bit different loading scenario.
Okay, on to some of the environmental and social impacts of our bridge. One benefit of our new bridge design is noise absorption. Compared to an open deck structure, our bridge will absorb more vibrations from passing trains due to the ballast and concrete slab on top. This is important as the DOT will be raising track speed, which of course will produce more noise. It's important for noise to be minimized as to not disturb the residential area that is so close by. A ballasted deck bridge also prevents debris and stormwater from falling between the structural members and onto the road below, creating potential hazard for vehicles. An open deck structure is exposed to air, so it will not be able to prevent anything from falling in between those members. That's about it from us. Thank you guys so much for watching and have a good day.